Thank you, Sean. All right. That looks a little bit like the first enterprise now, so okay. Anyway, okay, so for the next minutes, I'm going to talk about something we're quite proud of and we're quite enthusiastic about. And this is, we have developed kind of an optical chip which enables us to see biological systems in the way we do that, in the combination of things in an unprecedented way. So therefore, I titled it Making the Invisible Visible. And we were motivated. Actually, I could have, if I would have known the talk from Professor Oelfke, I could have used his as a motivation because he ended, one of the last slides was this, how we need to understand the mechanisms in order to really find out something about a better therapy. So if we want to make tailored therapies and we want to understand as much as we can, then of course that is very helpful in finding better therapies in the end. And that's basically what I've taken from the most recent Nobel Prize in Medicine. This talks about the oxygen levels in cells and their importance and how to change them by, for example, switching proteins. But the message, the take-home message is the more we understand about these mechanisms, the better, of course, and we are enabled to make completely new therapies. Okay, so I'm aware that most people here know what I'm talking about and why this is so important, but I still motivate that briefly. So basically, if you use a normal light microscope, and despite its age more than 100 years ago, in the sense of it was capable of already resolving on the diffraction limit, this is still the most used diagnostic tool, for example, in histology. So basically, we like to use our own eyes. Well, we also like to use computer programs which, for example, give us a nice, colorful blob of information and three-dimensional scanning. But most of the research work is still done, for example, with fluorescence microscopy. And the point is that a normal microscope can only resolve down to the level which is here indicated with the red arrow. That's roughly about 200 nanometers. We can discuss now the criteria, and it's a bit better or a bit worse, depending which technique we're using. But that's basically it. And if you want to understand biological matter, for example, if you want to look into the cells, into the organelles, into the mechanisms, we have to use something different. If you want to see viruses and details, if you want to see the proteins, and if you want to see the mechanisms in biology, we better have a technology which enables us to do that, and that's a technology which can resolve below the 200 nanometer level. So what we have developed now is exactly such a technology. And that's not the first one. There was a Nobel Prize in 2014 about super-resolution technologies, Storm, Stead, and Palm. But our technology has a couple of advantages. For example, it is completely biocompatible. It doesn't need labeling. We can use labeling, but we don't have to use labeling. And it is very fast. And I would like to briefly explain you why our technology is so fast, because we can essentially do video rate imaging of super-resolution pictures and videos of biological samples. So the idea we have is actually making a nanolight source. So what I try to explain to you how our nanoarray is working, briefly. So when we illuminate a particular metallic structure, which of course is embedded in the sensor, I've just taken it out, then we can create a very localized field. This localized field is shown here in the simulation. And if you just create the localized field, one of the tricks is how can we get the information from the near field into the far field. And at the moment we use an objective or any sensor which is far away means further away than the wavelengths of the light we're using, we have lost this information. Okay, so we have to encode this information somehow into the stream. And what we have done now is basically doing the following. As you see, we are modulating now our little pseudo pixel, and when we modulate it electronically or with an electrical current, then we also alter the near field. So basically the strength of our little confined optical field changes and is modulated with this. Okay, why is this helpful? And it's helpful now if you think about not having a single pixel, but an array of those pixels. It's shown on the left-hand side. This is, for example, now we are addressing a single pixel. We let it modulate. It's oscillating in its field, and now we can address other pixels. And this is the way we're knowing where the information comes from. So we can address our little nanolight sources at will. Here we just do it along the diagonal, but we could, of course, address them, any of them, at any time. And then the second important part is we can address them all at the same time because we can modulate them with different frequencies. And if we modulate them with different frequencies, we can, from the information stream, which goes to a signal channel, we can decode this information with the computer subsequently. Now, this information came from one particular local spot. That means we can use a computer in real time which reconstructs an image of that. And there's actually on the right side, there's such a sensor is shown, some test and trial sensor. So what we have done, for example, we have used, and that's quite recent, we have compared our technology against a higher numerical aperture microscope, and that's shown on the left-hand side. And what you see here are nuclear core pore complexes. And you see that on the right side, the technology which we have used, which is based on these pixels, which are modulated below, you see actually that we can resolve on the right-hand side the pores, and we can actually zoom in onto the pores, and then if you really have just a line across and try to fit the resolution, you find out that the resolution 2 weeks ago or 3 weeks ago in the meantime was about 21 nanometers. Well, 21 nanometers has been reached before, but nobody can use this technology with any kind of radio real-time imaging, and nobody can do it in biological matter with a deterministic method. So this is quite unprecedented, and therefore we are quite proud of that. That it's actually the talk I've taken from is from the last week's SFI summer talk at Lone. Okay, so just in order not to overdo my time frame here, so just let me say a couple of closing remarks. The technology here has a couple of advantages. For example, you can grow cells directly onto the sensor, or you can put your tissue on the sensor. We can also make an in vivo version of that, but in the moment it's an in vitro version. It has this very high resolution. It's very fast. It's compatible. In theory, you can retrofit microscopes with this. It's label-free, but we have used labels because for the contrast, but it's intrinsically label-free. We don't need the labels. And it's quite affordable. So the chips themselves are actually something we have now produced. We have made a little company called Pear Labs, and this company is now making all the necessary steps to commercialize the product. So we hope that a lot of people can use it. And in the framework of this SFI project, which we have at the moment, we also talk to a higher number of clinicians, actually, and we try to make new projects with them to show what we can see with the technology, which is helpful in finding out things on the biomedical side. Okay, so don't hesitate to talk to me if you're interested, or even just to have a nice chat. Just to wrap up, so this technology has 2 advantages. So what we do is shown here on the right side, but just let me say 2 things. We can do this very high spatial resolution real-time video imaging, but this can also be done in a cheaper version for early diagnosis. So we can make much cheaper version than a microscope, which can be brought to many places where early diagnosis is really purposeful in helping to create better situations for the patients. Thank you.
Fantastic. Thanks a million. So we're going from imaging the very small to imaging the very big.